Okay, hello guys. We're doing section 7.4 in my Vector Mechanics for Engineers Statics textbook. It's about cables. First kind of cable we're going to look at is a concentrated load cable, and the second will be a distributed load cable. Concentrated load cable is simply just where a vertical load is applied on a specific location on the cable. We're going to assume negligible cable weight, and we can approximate any portion of cable between successive loads as a two-force member. So now, looking at the free body diagram, we're going to represent the reactions at A and B with two components each. So you can see an AY component, an AX component, a BY component, and a BX component. We'll take a look at solving a concentrated cable problem later though. Our next type of cable is a distributed load cable. The load is distributed across the total length of the cable, as you can see with the free body diagram, not at one specific point. So looking at the free body diagram, we can see a cable with distributed load, as stated. So let's take note of point C and D. We see a tension force horizontal at point C, and we see a tension force tangent to the cable at point D. And then W, which is the distributed load, supported by the portion of the cable CD. It's downward. With these, we can draw a force diagram that, like we've used previously, to show the distributed load W downward, the tension load horizontal at point C, and the tangent tension at point D diagonal. This shows that the cable is in equilibrium. So the final type of load, it's a type of distributed load, but the final part is a parabolic cable. Simply, this is just a distributed load with a distributed cable load with something hanging off of it. Hence the Golden Gate Bridge and many other types of bridges with cables. So it's just a parabolic cable with cables or some type of load-bearing material supporting a horizontal load seen right here. Again, we know that the weight of the cables is small compared to the weight of this load, so we can neglect that. When doing a problem, we denote the load as W, so denote that as W, and express it as a Newton meter or pound feet. The second part to solving a problem like this would be to denote your coordinate axis at the lowest point. So in this case, it would be point C. So you can see the y-axis, the x-axis. Then use the equations given in the distributed load section to solve for the tension at D and the angle at which the tangent comes off. So as you can see right here, tension and then the angle. So we break it down similarly to how we would break down a distributed load cable. So I referred to some of those equations during my presentation, so I'm going to show you some of the key equations that we would use in a problem. Here are some of the more difficult equations that we'd have to use. So when solving for T, the horizontal tension, we use the tangent tension at D cosine the angle at D. Now let's solve a problem. One of the first things you will notice about this problem is that it is a concentrated load. as you can see, we have specific forces weighing down at each specific point. Now, what this problem is wanting us to solve for is the elevation of point B and point D. So let's keep in mind these measurements and these forces. So a better look at some of the free body diagrams we have here. Those are kind of difficult to see. So you can see two components at A, two components at E, and then an individual Y component at B, C, and D. So one of the first things we're going to solve for is determining the reactions at A. So we're going to determine AX and AY. We're going to use that by finding the moment around E. So let's go ahead and do that. Moment around E. We're going to need these measurements. Use these measurements. So, the moment around E. So let's write this down. So, we know that the AX component, so moment around E, equals 0, because it's an equilibrium. So let's first, so we have AX, and it is, so the AX component moving this way, the difference between it and the E component is 20 feet. So we have a force times a distance, 20 feet, using the vector rule in your right-hand rule. You know it's positive. So AY, what's the horizontal difference? So AY, it's going to be negative, is, so we're going to add these up, so that's 30, 30, 60 feet. Now let's go to point B. So it's 6 kips. You got 30, 30, and 10. It's downwards. So 6 kips. 30. So we have 40 feet. Positive. Next one's 12 kips. It's applied 30 feet. And your final one is 4 kips applied 15 feet. Okay, so you guys probably can't see that very well. So let's take a look. So you have AX applied 20 feet minus AY applied 60 feet from E. And then a 6 kip downward applied 40 feet from E. 12 kips applied downward 30 feet also. And then your final one is 4 kips applied downward 15 feet from E. And that's going to equal 0, because again, it's an equilibrium. So we're not going to get a straight out answer. We're going to get an equation. That's okay, because we're going to have another equation, and we can easily solve for AX and AY. So let's simplify this equation. At the end, you're going to end up with 20 AX minus 60 AY plus 660 equaling 0. So That's your final equation for that. We're going to use that later. So the next step is going to be finding the moment around C. So we're just going to consider the portion ABC. Just consider this portion ABC, as you can see by the free body diagram. Keep note that the difference in height from C to A is 5 feet. We're going to use that here in a bit. So, moment around C. It's going to equal 0. So, the first component, sorry guys, is negative AX applied, again, like we showed in the free body diagram, 5 feet from C. And then AY applied 30 feet from C. And then at point B we have 6 kips applied 10 feet from C. That's equaling 0. So let's take a look at this. We have AX applied 5 feet from C as shown in our free body diagram. The difference in height from A to C is 5 feet. We have AY applied 30 feet. We can see that in our older free body diagram. And then at point B we have a vertical load going downward of 6 kips 10 feet from C. That will equal 0. Again, this is not going to give us an outright answer. It'll get us an equation. But using our previous equation that we solved right here, we can easily solve for AX and AY. So let's simplify this. You end up with negative 5AX minus 30 AY plus 60. That's going to equal 0. So, solving this one, just a basic algebra problem, solving this equation and this one simultaneously, we can get AX and AY. So let's write down AX and let's write down AY. So solving AX will get you negative 18 kips, and AY will get you positive 5 kips. Now, knowing that the negative 18 is negative, we know based on a coordinate axis it is moving to the right. The force is applied to the right. And the AY, the force is applied upwards. So let's look at this. Negative 18 kips and 5 kips. This will help us here in a minute. So the next part of so looking back at the question, we see that they want the elevation of point B and point D. And we can easily find that by solving for the moment around B. Now let's look at a free body diagram. Free body diagram. This is just considering point A and point B. You can see an elevation from B to A. And you see the forces. So we can easily solve, since we know this force and this force, for the moment around B, and we will get our elevation. So let's go ahead and do that. So we have our AX, which is 18 kips, applied. So 18 kips applied from that height, YB, minus 5 kips, or our AY applied 20 feet from B. This is going to equal 0. It's an equilibrium. Let's write down this is moment around B. Okay. So solving for YB. This is our elevation compared to A. So our elevation compared to A will be 5.56 feet below A. So that is part of answer A. Let's circle that. So 5.56 feet below A. Now, that's not the whole answer because we need the elevation of D. So we can go ahead and do that. So to find the elevation of D, we're going to do it similar how we found the elevation of B. We're going to use the portion of the cable ABCD as a free body, and we're going to use the moment around D to find the elevation of D. So let's look at a free body equation, free body diagram. So this is ABCD. ABCD. Looking back at our other equation, other free body diagram, equations, we see some measurements and some forces. These measurements are going to be key to finding our moment around D. So let's get down to it. So, moment around D is going to equal 0. Okay, that's just basic equilibrium. So, first component in our equation, let's look at it. Moment around D. So we have 18 kips, a distance, elevation YD. So that is our AX component, and then since AX is a horizontal, our vertical distance from the component AX to D is the height YD. That is what we're solving for. So we have negative 18 kips, as we found, 18 kips. I'm going to just put 18K, and height YD. Second component is going to be our 5 kips. That is applied 45 feet. So our 5 kips is our AY component. It's going upwards, and it is 45 feet from our D component. So minus 5 kips, 45 feet away. 45. Third component is going to be our 6 kips. That's at our B point. That is 25 feet from point D. That B component is downwards. So 6 kips. And that is 25 feet away. And our final fourth one is 12 kips. That is at point C, going downwards, and that is 15 feet from point D. So we have 12 kips, and that is 15 feet from point D, and this whole equation will equal 0. So looking at this again, we have our negative 18 kips, which is our AX component, and that is a distance YD from D. So it's a Y distance. It's an elevation. Our second is 5 kips. That is our AY component, and that is 45 feet from D. Our third is 6 kips. That's point B, and that's downwards, and that's 25 feet from D. And our final is 12 kips downward at point C, and that is 15 feet from point D. This is all going to equal 0 because it's an equilibrium. So let's solve for YD. This will get our elevation in our second part of answer 1. So solving for this, we will get our answer will be 5.83 feet above point A. So let's get that. Let's circle that. That's important. Okay, so we're done with part A of the equation. We have our YB, which is 5.56 feet below A, and our point D, which is 5.83 feet above A. So let's go to B. Now, looking back, B wants the max slope and the max tension in the cable. So, let's this over. So one of the things we know, and they give us, is that the maximum slope occurs in portion DE. So, this should just be a basic trigonometric problem. So, looking at DE, we have 10. So, now remember, D is, it's not exactly shown well in this, but D is actually 5.83 feet above A. So that's going to be important, and that was our last answer, because we know that 20 feet is the difference between A and E. So the difference between D and E is 20 feet minus the difference between D and A. This is going to be important because we're going to look at we're going to do a basic trig problem. So let's draw this. This will probably help a little bit. So let's make this D, make this E. This is our triangle. So we know the difference between E and A is 20. So to find this, we need 20 minus the difference between D and A. So 5.83. It's not supposed to be negative. And we're going to get our vertical component of this triangle to be 14.17. 14.17. So that is this component. And then this component is actually given to us. So the difference between D and E in a horizontal sense is 15 feet. So just doing some basic trigonometric work here, we can find the slope as an angle. So this is 15 feet. So let's look at the equation. Let's look at this. So we have 14.17 as our vertical and 15. And we are solving for this angle. So we're just going to use tangent, opposite over adjacent. Let's write that down. Tangent theta equals opposite, which is 14.17 over adjacent, is 15. This is in feet. And we're going to get a final angle of 43.4 degrees. So that is the max slope. Max slope is 43.4 degrees. So the second part of problem B is the max tension. So we know that in this problem AX is 18 kips. So that's a horizontal load of 18 kips to the right. Now looking at a free body diagram, there are only two horizontal components, AX and EX. So we know in an equilibrium sense, AX plus EX will equal 0. So if AX is negative 18, EX has to be positive 18. So our horizontal tension stays constant. So we can easily solve for tension here. So the tension max, this is an equation here, tension max will equal horizontal tension, 18 kips, at point E, over cosine theta. And our theta will be our 43.4 that we just found. And this will equal, our tension max will equal 24.8 kips. So that is our max tension. So that is how we would do a distributed load cable. Just a basic example going through the process. Again, first answer, what is the distance, what is the elevation of point B? 5.56 feet below A. What is the elevation of D? 5.83 feet above A. Part B, what is the max slope? 43.4 degrees. What is the max tension? 24.8 kips. I hope this helped you guys. The best way to learn some of this is just do practice, do practice, do practice. Hope this helps, and thanks for watching.